par la date, qui est un lundi et pas un mardi, ce qui change tout. Je vous remercie d'être présents. Nous allons discuter aujourd'hui avec Yablonovitch, qui est l'orateur, de stockage de biomasse à grande échelle pour pouvoir stocker le carbone dans le sol. Et je lui laisse tout de suite la parole.
Merci, je suis désolé de devoir faire le séminaire en anglais. So, my talk will be about carbon negative technology. I started talking about this about 8 years ago, at a time when everyone wanted carbon neutral. They wanted things to be carbon neutral, but carbon neutral is not enough. We need to be carbon negative. And why do we need to be carbon negative? Because we like to fly on airplanes over long distances. I came yesterday from San Francisco. It's a useful thing to remember. For every kilogram of my weight, the airplane had to burn 2 kilograms of jet fuel. So I'm not carbon neutral myself. But we have to compensate by being carbon negative. We have another problem, and that is how to store energy from the summer to the winter. And there are not many good ways of storing energy for such a long period. And this is why I'm trying to justify that we will still need hydrocarbon fuels. So that's a second reason, is winter. And then a third reason is that there will always be some countries that do not cooperate. And if you don't want to go to war against these countries, you just have to suffer and just take out their carbon dioxide. So it means that carbon in the atmosphere will grow unless we can extract it. So we need a carbon negative technology. There's a further reason. In some models, there is a positive feedback from carbon dioxide. And for example, it might lead to permafrost releasing carbon dioxide, and then that could produce a thermal runaway. So the main point of this slide is carbon neutral is not enough, and carbon negative is needed. I think this is accepted now, but a few years ago, everything was about being carbon neutral, and I think now people accept a necessity to be carbon negative. So the question is, how can we be carbon negative? So there are a series of reports on how to remove carbon dioxide from the air. And so there's a report from the National Academy a few years ago. There's a report from the equivalent European Academy on negative emissions, they called it. It's a good name. Physics Today, can we capture carbon dioxide from the air? So now we are thinking of different ways of capturing carbon dioxide. One of them is to use chemicals, amines. So amine, this is groups that contain NH2, and these tend to combine with carbon dioxide, but they are projecting a cost of $600 per metric ton. So that becomes the figure of merit. How much will it cost to remove the carbon dioxide? And of course, this is a very high cost. I would say it's unacceptable. By the way, if I am speaking too quickly, just interrupt me and slow me down. Here's some information from the European report on different ways to be carbon negative. Manipulating the forests, increasing carbon in the soil, bioenergy, in other words, burning crops and then capturing the carbon dioxide and storing the carbon dioxide. This has an acronym BECS. So this is another way. There are certain rocks which actually capture carbon dioxide, but The kinetics is very, very slow. And then direct air capture, this is using the amines that I was talking about, and then fertilizing the oceans. So they considered these 6 possibilities, but somehow they overlooked the simple, what I regard as the simplest solution, which is the safe burial of agricultural biomass, which we call agro-sequestration. So that's what I'm going to feature. And I don't know how it is they had these 6 things and they never considered burying the biomass, but it's become more common now. So who originated this? So I understand I am in a physics department in this building, and so the justification why it belongs in the physics department is the first paper on this subject was published by the very famous physicist Freeman Dyson, and he published a paper in 1976, and he said, we need to grow trees and bury the trees. So this is the first suggestion of controlling carbon dioxide by burying biomass. And he, of course, is a very, very famous physicist, going back, I mean, he was friends with Feynman and so on. I had the pleasure of meeting him twice, and so he's a very brilliant person. So he had the first paper on the subject, but of course it was ignored. So what do we have more recently? We have a X Prize for carbon removal from the atmosphere. So now carbon dioxide removal is mainstream, and there's a $100 million prize to come up with the best way of doing it. And just to mention that the concentration of carbon dioxide is very small in the atmosphere, and just to pull out carbon dioxide, you're fighting against entropy because you need to concentrate the carbon dioxide, and so the minimum energy required is about 1/4 of a volt per molecule. Actually, it does require more energy than that. But plants, vegetation, they are receiving sunlight, and they can provide the free energy to pull the carbon dioxide out of the air. So this is very much a free energy challenge. So what are the plants? So the plants have all been worked out. The agricultural part has been analyzed because 15 years ago, at the Lawrence Berkeley lab, which is adjacent to where I work, they had the idea of biofuel. Biofuel turned out to be a bad idea. It's 15 years have gone by, and now people recognize biofuel is not a good idea. But they worked out all the agricultural parts. So, for example, in different regions, there are different agricultural plants that are preferred. In Illinois, which is the center of the American agriculture, there's a plant called miscanthus. In the Caribbean, it's better to grow this type of grass. Even in England, there's a crop that is very efficient. The point about these crops is that they are just producing cellulose, and so they're much easier to grow than food. Because if you grow food like maize, then the insects like to eat the food. So it's much harder. You have to be more careful in how you grow it. So let me calibrate you a little bit. When we grow maize in America, we can, or sugar cane, or similar things, we can ask, what is the efficiency of converting sunlight into carbohydrates? So the way the calculation is done, you have a joule of sunlight, and you ask how many joules of carbohydrates is produced in the plant. Now, if it was a solar cell, and by the way, my background is in solar cells, the most efficient solar cells are about 29% efficient. The plants that we grow in agriculture, the ones that produce food, the best are, at least in America, it's 2% efficient, because in America we grow maize. But if you go to the Caribbean, we grow sugarcane, can be 4% efficient. But it's still far from what solar cells can do. So if we grow cellulose, which are these plants, we can be more efficient than growing food. So these are the different plants. And pardon me if I use American units, an acre is 0.4 hectares. Hectare. 0.4. So roughly, when you grow cellulose, it's 3 times more productive than growing maize. And so this is the typical chemical formula for carbohydrates in plants. You have 44% by weight carbon, and then you figure this whole thing out, and you can produce 10 or 20 or even 30 tons of cellulose per hectare. So this is pretty good. Now, the person who got me into this, he sort of was one of my mentors. He's not very famous. His name is Al Rose. And when I started working on solar cells, he was a consultant in the company where I was working. And he came from RCA, which was the company that created television. And in fact, he was the inventor of the Vidicon camera. But by then he was old. I was young, he was old. And one day he told me, oh, you're interested in solar cells. Well, don't underestimate agriculture. He said, go look up what is the cost for a joule of carbohydrate versus a cost of buying a joule of gasoline. So it was a time when the price of gasoline was very high. And he said, go look on the Chicago Board of Trade. So the Chicago Board of Trade is where the farmers sell their crop. And you can look up the price of maize and other important crops. And with some manipulation, you can convert it into joules. And I was very shocked. He had already worked this out. He tricked me. He had already written a paper on this. The cost per 100 megajoules was roughly the same whether you're buying gasoline or corn. Corn is what we call maize in the United States. So surprisingly, agriculture was able to produce fuel at that point in time. The price of fuel had gone up, and so the price of fuel was roughly the same as the price of agriculture per megajoule, which is somewhat surprising. So this told us not to underestimate agriculture. In fact, since then, I have been convinced that my research on solar cells, in the end, we will compete with agriculture. So there have been studies of energy. They were very interested in biofuels, and they studied what can you use and what are the different crops and so on and so forth. There are many Department of Energy studies. This is another one, how to have enough agriculture for 1 billion tons to make biofuel. Of course, I will explain it later on why the biofuel was a failure. But at least it told us a lot about the agriculture. So then the reason I'm here today is that 2 months ago, myself and my co-author published an analysis of how we can be carbon negative, how we can pull carbon dioxide out of the air using vegetation and using agriculture. And the secret is it's very easy. The agriculture is very efficient. It gets more efficient every year because we've been doing agriculture for 10,000 years. By now, we're quite good at it. And then the question is, where do we put the plants? Where do we put the agricultural products? And it's not so easy to preserve them. So the main new thing I will try to describe is how to bury the agricultural product in such a way that it will be preserved for thousands of years and will not decompose into carbon dioxide and methane. Simple burial does not work because you get this decomposition. So you get back the carbon dioxide, and even worse, you get back methane. So it's not good. There are microbes, anaerobic microbes, that for whom this is an exothermic reaction. And it's very interesting if you think about wood. Wood is about 70% cellulose and about 30% lignin. And sometimes I know in my backyard, in my house, I sometimes am digging in the yard and I find an old board that the contractors, the people who built the house, left behind an old board. Maybe you had the same experience. And you dig up the board and you notice the board hardly weighs anything. It's very lightweight. Who's had such an experience? Am I the only one? So some of you have had this experience. So the reason is that the cellulose is destroyed by microbes right away, and then the lignin is very hard to decompose. It's very hard to turn it into biofuel. It's very stable. It provides strength to the wood, and it stays behind for a very long time. So if you bury wood, you bury 70% of the wood, but 30% remains buried. And so you have a form of sequestration. There are now many companies in the United States, and I think certainly in Europe. I know at least 7 companies in the United States, startups, whose business model is to bury wood, which is somewhat surprising. But I would claim that this is not a great idea because it's inefficient, because only 30% of the wood is sequestered, because the part that's lignin will last a long time in the ground. The part that is cellulose goes away. So it's very inefficient. So then we have to get a little more scientific. So we have to introduce a concept called water activity. So water activity is not exactly the same as relative humidity, but it is the relative humidity that is in equilibrium with solid food, for example. Let's say you have a steak like this. You could ask, what is the relative humidity of the steak? And so it has a name. It's called water activity. So it's a way of describing the relative humidity of a solid material. Now, so here we have a steak. If it's very dry, we will say the steak has a low water activity, and it will be very difficult to decompose. So how do we preserve food? We keep it dry, and we might use salt, but the most important thing is just to keep it dry. So this is recognized by government authorities who are responsible for food safety. So if you have something in the supermarket which is very dry and sealed off against the atmosphere, they will say, okay, it's safe to leave it on the shelf of the supermarket. The key is that the metabolism comes to a stop when you have less than 60% water activity. So water activity, it's similar to relative humidity, but it applies to solid food. So we can ask for different types of carbohydrates, how do we get below the 60% water activity? And so you have to remove water. So if you go below 12% water content, you're safe. And so these are hardwoods and things, grasses and miscanthus. Roughly speaking, you get 10-12% water content. You're safe and it will not decompose. Now, how do we get below this 60% water activity? We can make it very dry, which I just showed you, remove the water.
Could you define with an equation what water activity is?
Yes, it is the relative humidity in equilibrium with a carbohydrate or food. Okay, so that if you say, what is the water activity of the steak? You say, well, if the relative humidity, let's say, we dry out the steak, So the relative humidity in equilibrium with the steak would be such that you, above relative humidity of 60%, the water will condense on the steak, and below, if you have relative humidity below 60%, the steak will give up some of its internal water.
So it's like the partial pressure?
Yes, it's like the partial pressure, and it's very analogous to relative humidity, but it doesn't apply to air, it applies to solid materials. And so, for
My
example...
problem is that I don't know the equation for relative humidity, so
Okay.
I don't have this one.
Okay, but it's reported in the weather forecast, or today it's a relatively humid day. We know this. It's a rather important concept. Suppose, for example, you want to put food on these in the supermarket. You wrap it up, and then you tell the Food and Drug Administration, you tell them that you have dried the meat, so it now has a water activity below 60%, and they say, okay, it's safe to leave on the shelf in the supermarket. And this applies, of course, not just, I give us a crazy example is to use steak. I'm just trying to make a point, but you could be some pastry or any other carbohydrate. You could have the same concept.
Is it temperature dependent? Or
It-
if you compare, say, the relative?
Yes, it's a very good question. Is it relatively temperature independent? Yes, it's surprisingly temperature independent. Obviously, it depends slightly on temperature, but it's a sort of a safety level. And of course, if you make it cold, it's safer. Here's another way to solve the problem, and this has been known since Babylonian times. If you want to preserve food, use salt. And what are the best salts? So let's talk about sodium chloride. Well, sodium chloride will not get you to 60% because sodium chloride will get you only to 75% relative humidity. But if you use magnesium chloride, then it's good enough. Magnesium chloride will get you below 60%. So it's even more effective. Now, why did they use, in Babylon, they were already using salt, because at 75%, it's already helping a lot. But if you want to completely stop metabolic activity, you have to drop below 60%. And these salts will do it. And why is salt good? Because salt reduces the concentration of water. It displaces water molecules. And if you have a lower concentration of water molecules, you also have a lower vapor pressure and a lower water activity. And then if you use a divalent salt, like magnesium chloride or calcium chloride, it takes additional water molecules out of circulation. So the divalent salts, magnesium chloride and calcium chloride, are even more effective. So you can use dryness and or you can use salt. Both are very useful for preserving biomass. And the calcium chloride is a very common salt because it's used to melt ice on the highways. And so it's something that if we drive in the winter, we're all somewhat familiar with calcium chloride. So calcium chloride is extremely effective at preserving food. So that's sort of like the science part. It's not too much. It just has to do with a little bit of chemistry. To preserve food, you keep it very dry and or you add salt. That's a simple idea. Okay, what do you do with the biomass? So the biomass would be similar to some of the plants I showed you. Maybe it has cellulose. And what you do is you bury it in what we call in America a landfill. I don't know what's the word in French. Landfill? Say it again, please. Décharge, okay. So the most modern landfills in the United States, they're sealed with 4 millimeters of polyethylene. So it's very thick. The purpose is to prevent the garbage or chemicals from the garbage going into the water table. But we want to use it in reverse. We want to prevent water from going into the biomass. So we have in mind that we will bury the biomass in a landfill. And the purpose of the landfill, the purpose of the polyethylene is to keep it dry and to keep the water out. And at 4 millimeters of polyethylene, some water will diffuse, but very, very little water will diffuse in, and it will last for a very long time, thousands of years. So what is the size of the problem? So this is something that is very well known, is that we're producing 40, maybe now it's 50 billion metric tons of carbon dioxide every year. We have to pull it out, and we want to use agriculture. So what is the available land for agriculture? So there's quite a bit. The traditional row crops, which are wheat, corn, rice, etc., they represent 11% of the world's land area. But many of the cellulose crops, they don't need the best land. And if you add the ranch land and the other and the forest land and so on and so forth, it's you can easily find enough land to grow this much cellulose. But let me tell you how big it is. If you want to treat it as a row crop, it would represent about 2% of the world's land area. So it would be a very big crop. It would be one of the biggest crops, 2% of the world's land area. So, often when I speak to Europeans, they think, well, it's too much. France cannot do this. But don't expect a European country to do this. Even the United States cannot do this. The United States has 6.6% of the world's land area. So it's an international problem. It must be solved internationally. There will be a need for imports or somehow paying farmers in other countries. So if you remove half of the CO2 every year, you're doing quite well, because the other half seems to disappear by itself. And you can use 1/15 of all agricultural land and there would be enough. So then the question would be, how much will this agriculture cost? Now, we're actually quite good at agriculture. We've been doing agriculture for 10,000 years. And we know that these types of biofuel crops, they don't need so many inputs. They don't need so many fertilizers, insecticides, and so forth, because they are not food. So we can look at the productivity of the biofuel crops. And we can look at these prices. All of this in the United States, the prices are set in Chicago. And pardon me if I use some American units, but it's roughly $500 per acre. And you can sort of figure out what is the cost of growing these different plants. So the cost of the agriculture is very accurately known, because it is currently being grown for purposes of biofuel. So we know the cost. There are other crops which are slightly more expensive that also are being pursued by some people. But this is one of the more accurately known numbers, is what is the cost of growing these crops. Now, it works out to be $30 per ton of CO2 just for the growth, but then you have to bury the biomass, and that works out to be another $30 a ton. So roughly speaking, it works out to US dollars per ton, per metric ton, to grow and bury the biomass. Now, if you accept that, then what if you would ask, I will buy gasoline and I will pull out the carbon dioxide from my gasoline. So what will that cost? I have now in American units, but I can give it to you in European units. It would be approximately 15 euro cents per liter. That's what it would cost to remove the CO2 from your gasoline. And let's estimate the effect on the world economy. So the world economy is roughly $100 trillion. And this would mean if you did this, you would set back the world economy by 1.2%. So this is not the end of the world. And the reason it's so cost effective is that agriculture is very efficient. We used to have everybody working in agriculture, and now we have only about 1% of the population working in agriculture. So people don't understand that agriculture has improved over the many years. I have here some data on the productivity of land. This is not per dollar, this is per hectare. The productivity of land in underdeveloped countries has doubled over a 50-year period. This is extremely typical. I have, on the next slide, I have data going back to the 1700s from the UK. And what is the yield per hectare? And between 1800 and 1900, the productivity of farmland in England doubled. And then from 1900 to 2000, it doubled and doubled again because artificial fertilizers were invented with the Haber process at the beginning of this period. Here's the Haber process. And so in the past 200 years, the productivity of agriculture has increased by 8 times. So this is something we need to get used to. There's a Moore's law for agriculture. It's constantly getting better. And this is the another way of measuring it is how the amount of land needed to produce food has dropped over the last 100 years. And of course, it dropped very substantially. And this is why Malthus, he was the philosopher who lived about 200 years ago. He thought we would never catch up with the growing population. And of course, we have easily caught up. So I sent this paper to be published, and the referees said, well, it's a good idea, but you need to have some proof. So maybe some experiment in nature that has shown that you can preserve agricultural products, that you can preserve it for 1,000 years. So it turns out there is such an experiment that occurred 2,000 years ago in Israel. And this was by King Herod. And this is a very famous mountain adjacent to the Dead Sea. Back here you can see the Dead Sea. And adjacent to the Dead Sea, there was this mesa. The Dead Sea is maybe 500 meters below sea level. And the height of this mountain is such that the top of the mountain is right at sea level. So he built a palace. It's not exactly a palace, it was a fortress, because like every king, he was afraid of being overthrown. So he built a palace in this place. And it also, a few years later, when the Romans were conquering Israel, the last of the holdouts were famously, they were attacked by the Romans. And they held out for 2 years, and then the Romans built a ramp on the other side of this mountain, and they saw they were going to be defeated, and they all committed suicide. But the important thing is King Herod's palace, because in this palace there was an excavation in 1965 by archaeologists, and they found in the palace, they found some seeds to the date palm tree. And so this is quite interesting. This is what the seeds look like. They're rather big seeds. And they were put there by King Herod. And then the archaeologist was this guy, Yigal Yadin, Israeli guy. And in 2005, a medical doctor at a hospital in Jerusalem heard about this, and she was able to obtain these seeds. and she sent them out for carbon dating, and they were 2,000 years old. And then she went to an agronomist, this lady, an agronomist, and said, please plant these seeds. And she planted these seeds, and they germinated, and they gave a small tree, which now becomes an 18-year-old tree. Okay, so this, of course, the climate is very, very dry. This is one of the driest places on Earth. It's a very dry climate, and the seeds were preserved for 2,000 years. So I think this is proof the DNA was preserved, etc. So it was the natural experiment that the referee wanted. So I was able to persuade the referee, and we got the paper published. And let's see, I think I showed you this slide already. But let me summarize what's needed. So I think we've proven that if you keep the biomass dry, it will last for 1,000 years or longer. And so what are the prerequisites for solving the carbon crisis, the climate crisis? You need something that is scalable, that can be very large. Of course, agriculture is very scalable and also becomes more efficient every year. The cost is very easy to work out because every country publishes agricultural statistics, and the construction of a modern landfill also the cost of that is well known. The modern landfills use 4 millimeters of polyethylene. And then the stability, long-term stability, I showed you that the date palm seeds, they lasted 2,000 years. So it's a proven sequestration, essentially using dryness. And another requirement is predictability. So if we have a new idea and we have to do experiments, some would say, well, we have to wait hundreds of years to validate the new approach. But we don't have to wait because this has already been validated by this natural experiment of the date palm seeds. So we don't want to wait hundreds of years. So we need predictability. There might be other good ideas, but we might have to wait a long time to be certain that they work. So let me summarize, is that we do have a carbon dioxide problem. Being carbon neutral is not enough, and we need to be carbon negative. Agro-sequestration, this is the name we've given to this, so we think it's practical, it's cost-effective, etc., etc. And so I'd like to invite questions and have a discussion. I'll tell you candidly, this is my first time giving this talk in Europe, so I'm pleased to tell your friends about this, and let me invite questions. Thank you very much. Since it became very warm in the room, maybe we should open more windows. Open the door now.
I think we have one question there.
What about the competition for land area between food growing and crop sequestration?
Okay, so the question is about competition for land area. In Europe, land has always been very important for agriculture. But in many other parts of the world, there is plenty of land available for growing new crops. Even where I'm from, which is Canada, there are many farms that used to be farms when I was young. Today, the farms have been abandoned because the climate is not so good for farming. They cannot compete with the farms in the Midwest of the United States. Also in New England, which has a similar climate as Canada, many farms have been abandoned. There is lots of farmland available using today's technology. But one of the arguments I gave is that in the future, we will have even more farmland available because the amount of land needed to grow food becomes less and less every year. But I'm not using that. I did the analysis based upon existing technology of farming and existing farmland that's available. But in the future, we'll have even more farmland available.
Yes, one question about this efficiency of agriculture. Of course, it was also due associated with a strong intensification of introns and so on. So with a more conservative agriculture with less pesticide and so on,
Yes.
we may come back to more extensive agriculture. But I have mostly another question. It means having a huge quantity of chloride brought onto land. So how can this be produced, and can we be sure that on several thousand years it will not damage phreatic,
Yes.
both underwater and so
Yeah.
on?
So I appreciate the question very much. You have two questions. Remind me of the first question.
No, but it's not so important. It's about the stabilization of efficiency of agriculture.
Oh, yes, that's right. And you're worried that we will become less efficient in agriculture. So one of the parts of this paper was to calculate the carbon efficiency. In other words, if we sequester 100 tons of carbon dioxide, how much carbon dioxide is required to produce the fertilizer and the farming and the farm machinery and so on and so forth. So this is something that has been worked out, and it's been reported in many papers, agricultural papers. When you sequester 100 tons of carbon dioxide, you produce 6 tons of carbon dioxide in the course of farming. So that means the agricultural machinery producing the fertilizer and so forth. So this is just something we have to deal with. But it's somewhat balanced because by growing these crops, we're also putting carbon into the ground through the roots. And so you can say, well, the efficiency is 94%, but it could be, if you include the roots, maybe the efficiency could be slightly over 100%. So it's, I think that question is answered in the paper. Now, the second question?
It was about the huge quantity of chloride.
Oh, yes, okay, a very important question. So I get many complaints about the chloride. So let me just say that it's optional. If you dry the crop enough, you don't need the salt. So now you have a cost trade-off. Do you want to use salt, or do you want to do more drying of the crop? And so they are. It's just one exchanges for the other, and the cost of the calcium chloride. Well, it's not very high, but we don't have enough production capacity. We'd have to increase the production capacity of calcium chloride. It comes in the United States. It comes from underground. There are underground pools of calcium chloride. Also, somebody just told me, was this Philippe? Told me that he has a relative who mines magnesium chloride, or mines or extracts magnesium chloride from.
Dans les marais salants, l'eau mer qui reste après le ramassage du sel, elle est riche en chlorure de magnésium. On a des eaux riches en chlorure de magnésium dans les marais salants. Magnesium chloride rich water is natural.
So, but the salt is merely an option. It's just a cost trade-off.
Thank you for the talk. I feel that it's very important, this kind of talk here, because we are not used to having them. It's important questions to tackle. So thank you. I feel that you are very focused on carbon dioxide, and it makes your assumptions quite optimistic, because we have also either other physical limits, and for example, in agriculture, we are confronted with water, with just the water disponibility, the soil erosion, the needing of phosphate for fertilizer, for example.
Yeah.
I mean, how do you tackle these other physical limits in your research?
Yeah. So I mentioned about the carbon efficiency being 94%. Now, in that 6%, we include the different types of fertilizer. Okay, the most important fertilizer, just nitrogen fertilizer. So that produces carbon dioxide. When
But
we,
you are limited by the physical amount of phosphate that you have on the
Yes,
reservoir.
yes,
You are
yes.
limited by the
Yeah.
disponibility of water.
Yeah.
This is
So
not
we-
carbon.
we take all those things into account, and that ends up being part of the 6%. For example, when we produce fertilizer, that is accompanied by nitrous oxide. So for the nitrous oxide, it's a greenhouse gas. And so we say, okay, how much carbon dioxide do we have to remove to compensate for the nitrous oxide? And so we have tried to take all of those factors into account.
For these landfills that are supposed to last 1,000 years, what are the requirements where to put them? I mean, with your experiment, that's a very special climate, very dry.
That's true.
Is it hard to find
No,
suitable sites?
yeah.
Or-
So we don't rely upon the climate to preserve the biomass because we create an artificial climate inside the polyethylene envelope. And this polyethylene envelope is the current practice in modern landfills. So the reason why it lasts 1,000 years has to do with the diffusivity of water through polyethylene. There is a finite diffusivity. There's a finite amount of water coming in. And if you dry the crop, it will absorb the water that diffuses in, but it will stay below 60% water activity for a certain number of thousands of years. And then after that period, there will be enough water that will come in that it will go above 60% water activity. So this is how we can project the lifetime. We don't look for a special climate. We look for landfills that are constructed in the most modern methods, which are already using this 4 millimeters of polyethylene.
And is there anything that will attack the polyethylene, or it'll basically last well over 1,000 years?
I think underground, what will attack polyethylene is sunlight. And underground, I think it's very, very stable. It's been investigated. And so you bring up an interesting question, is what have we overlooked with the polyethylene? And I think one should be, one cannot be 100% certain.
In terms of sequestration of carbon, there's also the biochar solution.
Yes.
Can you compare the advantages
Yeah.
from each other?
Yes, the biochar is not very cost effective because let's say you bake some biomass, then some gases are emitted during the baking process, and you end up with only a fraction of the original carbon is sequestered. So the carbon efficiency is very important. Suppose, for example, I would bury wood. It's effective, but only 30% effective, because 30% of the wood is lignin and will last a very long time. So for every one of these techniques, you have to look at the relative cost effectiveness. Biochar works, but it's not so cost effective. Let me contrast it with, I promised you to analyze the biofuel case. So in the biofuel case, we start with carbohydrate, which is what we grow. And because it's already partially oxidized, we need to grow 2 hectares of biomass in order to get the equivalent fuel from 1 hectare. So we are twice, by burying the carbohydrate, we're twice as effective as producing biofuel, because biofuel, you're starting with the carbohydrate being already partially oxidized. So you end up with a factor of 2. So it's not that there's anything wrong with biofuel, it's just not competitive compared to burying the biomass, where 100% of the carbon goes into the ground. And so you have to do these analyses. There are different options. They all work, and then it becomes a cost question. The biofuel always ended up too costly because you needed twice as much agriculture. And the same with biochar, is that in manufacturing biochar, things become, you're wasting a lot of the carbon. The other point to make has to do with this ability to if you use agriculture, to use 100% of the agriculture. And this method, all of the carbon that is captured by the plants, all of that ends up in the ground. And so that's an important factor. Go ahead, please.
Yeah, thanks for answering that question. I think for the cost to be an efficient metric, it has to be fair, and one has to factor in all the externalities, whether negative or positive. And I think with biochar, one of the positive externalities is that it helps the soil store moisture. So we can turn a land that was carbon positive into a carbon negative one when you insert biochar. So maybe it's not long-term scale as the solution you explained today. Yeah. But on some shorter time scale, biochar can be an effective method.
Well, I think you have to analyze everything. We are also, the agricultural part is also carbon negative because we're putting roots in the ground that will last a very long time. So it's somewhat similar to that. One of the problems with the biochar, it eventually oxidizes and decomposes, so it's really not that long term. But I don't want to say negative things about competing approaches. I've already said enough negative things. So I would say, okay, go ahead, figure out the externalities, and we tried to take those into account, and they ended up relatively small. But let's I don't want to put anyone out of business if they want to do this, or if they want to capture CO2 using amines, or let them go ahead and let people decide which is the most cost effective. Yeah.
I have a question, please. I have a question on the long-term sustainability of your approach here. So the landfill will take space, right? And will take space, over the year, and how, and possibly could compete with the usage of the land that you're using for.
Okay, so we get that question very often. The answer is, when you have finished the landfill, you put soil back on top of the landfill and it becomes a farm again. And so we should not think of it as taking space. It's just taking space only underground, but the agriculture continues above the landfill. Who's next?
If there's a case of leak, for example, in the polyethylene, what is the speed of the decomposition of the crop? How do you compare it with the wood and the lignin that is quite safe?
Which is quite safe?
You said the lignin doesn't decompose.
Oh, lignin.
So it's safe. In case of accident, you know what.
Of course, the biomass, we don't really care which biomass you use. If it comes from wood, it will have 25% lignin also, and that will be very permanent. I just have to share with you a story that happened a few years ago. My wife and I were tourists in northern England, and we said, well, we're here in northern England, let's go to Hadrian's Wall and see if there's anything. And you'd think that they would, it would be a big archaeological site, but it turns out that they were not treating it in any special way. Is that anyone can come and dig at the fortresses that the Romans built in the northern part of England. And they had, at that time, which was only maybe 8 years ago, they had discovered pieces of wood in the garbage. And you have to understand, the Romans did not have paper. Paper was invented in China, maybe 700 AD. And so the Romans had no good way of, nothing like paper to write on. So they wrote on strips of wood. And they found some strips of wood with messages that were written by the Romans in the fortresses. And one of the messages was, "We're out of beer, send beer." Another message was a birthday greeting, and so on and so forth. These were written in Latin. And so those strips of wood were preserved. And of course, it was anaerobic. It was in with the garbage in these fortresses. And the way to understand this is the same as digging up old wood in the ground and finding it's there, but it weighs very little. It has very little weight associated with it because the cellulose is gone, the lignin is there, and the Latin writing is available on the lignin. So that's the way to think about different things. Now, I think the other part of your question had to do with what happens if something goes wrong.
Because with the wood, we have a 30% safeness.
Well, you preserve
But with the
30%.
composition,
Yeah.
but with the crop, only how fast?
No, we still have the 30% with the crop as well, because the crop has lignin too. But the other point to make is that you probably want to monitor these things, and if you monitor them, you can do some type of repair. You can, for example, inject salt, which maybe was too expensive to inject, but just to take care of a water leak, you could probably inject some calcium chloride, or just rebury the biomass into a new landfill. So there are ways of overcoming some of the problems that might occur. I think I had a list of requirements: cost, permanence, and so on and so forth. I did not include repairability in the list because I don't really expect that if things are deep underground that they're going to need to be repaired, but it's always possible.
Thank you for the talk. I had another question. So the first is, I didn't understand if you have made the energy balance of the operation and whether how much energy you spend per ton of CO2.
Yes.
That's the first part of the question. And the second part of the question is, why can't you do that, the same thing, with the crop residues instead of growing new crops and stabilize them into carbon compounds?
So just to answer the last part first, we're completely agnostic with regard to the crop. So you can use any type of biomass. That's fine. With regard to the first part of the question, which is the energy balance, we have done the energy balance. We've done it based upon the carbon budget and also the dollar budget, the financial budget.
The dollar budget is not that...
Of course, it's not unless you're actually doing it, then it matters. But they're both very similar. The inefficiency is about 6% in both cases.
No, I mean, how much energy do you need to
So we've taken into
invest per ton of CO2 sequestered?
Right. We've taken that into account through the carbon budget. So the carbon budget includes, for example, farming. So you have to provide gasoline for the farm machinery. You have to provide methane for the fertilizer, and so forth. So we took all of these factors into account, and it shouldn't be surprising that they only add up to 6%, because after all, agriculture is quite efficient and produces energy on its own. So the answer to your question is all of those costs that you're concerned about, even if we do it based upon the carbon budget, not the financial budget, they all add up to about 6%.
Okay, maybe the last question, otherwise we can stop now. Okay, thank you again.
Thank you very much.